this is just to show that this is an old age interaction. This here is the crown gall, and that's agrobacterium, and many of the talks used that method, right? But one of the oldest, billions of years ago, is the chloroplast. And similar to the non-climate change believers, right? You also had the non-bacteria making the chloroplast believers. But nature is the best scientist, right? It repeats itself. So after millions of years, so this is billions, millions, an interaction between Pollonella and Cyanococcus-like formed again, and does exactly the same as the chloroplast in plants. So one of the questions that keeps coming back, and we've heard Derek Inza and many people talk about the transferability of our technologies, was if these associations and these bacteria are in the soil, right? Why are all of you guys here today? Why are people still working on plant science? Because then agriculture should flourish. And if you look at reasons, right, one of the things which people are showing now over and over is that we are losing our microbiota, or the microbiomes in the soils. And this is due to many reasons. So why is the numbers decreasing currently? And why is that rate just increasing and increasing? Over-reliance on agriculture, that's one, right? Again, climate change is going to contribute to this decrease in soil microbial numbers. Over-reliance on fertilizer, we heard that yesterday when one of the speakers showed us the graph where we will have to increase our fertilizer production and our over-reliance on herbicides and pesticides. So our soils are going to be more and more degraded, right? And if you look at here, this is where I'm from, right? So it shows that very degraded soil. I've actually been into the field and I've seen the degradation, and it's quite scary. So if soils lost the good bacteria, right, and there is that balance between the bad and the good, then under abiotic stress and biotic stress, these plants can no longer perform well. So that's one of the things which I'm thinking. And so this is a lentils in the field, and this is showing when you take lentils and you just put it straight in the soil, then you get this. But when you add rhizobium to it, you get the lentils growing well. So this shows that even these microbes are in the soil, but they're not there in high enough numbers. So so now we will have to apply microbes to our soils or to our seeds to give us that, to let our plants look normal, essentially. So one of the issues also is that the environment is dynamic, right? And that's why we can't translate many of our research. And this paper by Penday shows that it's just crazy. So if you're gonna focus just on one environmental stress, like I used to start, I work on metals and nutrients, then you're gonna answer only one piece of the puzzle. But when you take your plants into the field, there's that dynamic environment. So heat will be there, drought will be there, there will be pathogens, right? And those interactions will drive you crazy. If you think, oh, maybe the pathogen will decrease the susceptibility to drought, right? And then you come there the next day, and then you see your plants actually doing better, because there was this reactive oxygen species and signaling, and so that geared the plant to perform better. So that dynamic environment tells us that we will have to move to dual stresses, and even 3, 4, 5 stresses. So in South Africa currently, we are heading towards 60 million people, right? And food production is decreasing. So we will have to find ways to sustain our food production. And we saw, the gentleman showed yesterday, the increase that we're going to rely on fertilizer. And we harvest a lot of those phosphate rocks that's going to run out. So South Africa, why did I start this research? Because South Africa is one of the top mining countries. And if you look at Johannesburg, more than 4 million people are affected by the mining in the form of acid mine drainage. So this is a real problem. And that mining leads to more degradation. And these degradation are in our reasons where we need to produce more food. So I think climate change is going to make this worse. That's what I'm thinking is going to happen. So I found this paper, which told me that I'm not on the wrong path, because what they showed was that these hyperaccumulators, metal hyperaccumulators, harbors some of the microorganisms which assist. So because our hypothesis was that we should look at plants that can resist a variety of environments, or they are tolerant, like our weeds. And so we targeted the weeds because they grow everywhere, right? And so we looked at a variety of plants, and these have now increased to plants from the close to the Kalahari Desert, plants found at the beach. So this is just an excuse to go to those environments, right? So these are just 3 of the plants. One is Echium plantaginum, hairy fleabane. This is probably in the US as well. This one we've seen, which is Medicarpa lupulina, and this is quite tolerant to drought. So we isolate the endophytes from there. We are now also doing fungal endophytes, and then we use that to improve plant stress tolerance. So one of the projects that I'm going to talk about is the one where we isolated bacteria from Echium plantaginum. Echium plantaginum also grows in low, where there's low fertility, and if you see Echium plantaginum in the field, it's you don't see the humic acid, so the soil is very poor in nutrients. So we targeted that, and we isolated one bacillus strain, and we called it Bacillus CP5, and the closest hit was Bacillus firmus strain NBRC, and this one is also sequenced. So Bacillus firmus CP5, we further characterized it, so we know that we're going to run out of phosphate rock, right? So we need phosphate solubilizing bacteria. So one of our assays, we saw that CP5 solubilizes phosphate, and then so we wanted to know why, and we added bromocresol purple, and when you see this orange from the purple, then the pH is now further decreased, and that's organic acid production. And then we also did zinc oxide, so zinc solubilization. And we saw that CP5 doesn't like the zinc oxide that much, but there's still solubilization. Then we looked at IAA content, because many of this plant growth promoting bacteria, they have hormones, right, that assist in plant growth. So IAA, and we saw that Bacillus CP5 is producing IAA via tryptophan, so tryptophan dependent. So then we also looked at ACC deaminase, which cleaves the precursor, which cleaves ACC, which is a precursor for ethylene. And ethylene goes up when there's stress, and you'll see in the next slide. So this is in hours. So we grew the bacteria in media lacking a nitrogen source, and then we added ammonium sulfate, and you can see the bacteria likes ammonium sulfate as the nitrogen source. When we add magnesium sulfate, we didn't see that much growth, but when we add ACC, we saw that the plant can cleave ACC. And so this shows that the regulation of ethylene. And that regulation is shown here by Mohammed. So if you have ethylene production increase under stress, the plant growth will be suppressed. So you would want to reduce that ethylene, and that's where your plant growth promoting bacteria comes in, and they decrease that, and so plant growth is stimulated. And then we look at germination. So we choose Brassica napus avigane, and we choose this because we published a paper where we showed that avigane really germinates poorly. And so we use that as our model for germination increase. So we saw that when we add antimony, which is one of the metals which is produced from South Africa, then, and there's very few papers on antimony and plant interaction. We saw that the plant didn't perform that well, germination, but when we added Bacillus firmus, we increased the germination and even under antimony stress. So then we wanted to see over time what happens. So this is days, and we saw that when we add Bacillus firmus, we increase it even from 8 days up until 14, and we saw the same in the presence of antimony. And then we checked dry weight, and we saw the same trend, and then we checked the cell death. So here we added Evans blue, and if there's cell death, then the cells will take up the Evans blue. And so then you crush and you release the Evans blue, and then so if you have more Evans blue, it shows there's more cell death. And we saw that the same trend as our dry weights. So we wanted to know why do we see that regulation? And then we did ICPI genomics, and we saw that antimony decreased almost all of those nutrients, macro and micro. And when we added Bacillus firmus, CB5, we could increase most of the nutrients. And this one drove me crazy, the iron signal, right? And under antimony, we saw that we could increase the uptake of most of these nutrients. And we did the same for the leaves, and we saw a very similar pattern. So seeing is believing, right? So one of my students made a nano tracker, and so she used quantum dots, and these quantum dots will give off fluorescence at certain wavelengths. And so she transformed CB5 and then treated Brassica napus avigane with the bacteria. And she saw that in the roots there's more fluorescence, in the leaves and in the stems. And this is some more autofluorescence, and I think I have a way to deal with this, because the quantum dot, the peak for the absorbance of the quantum dot is quite broad, and this is one that we bought from Sigma, and so we can sift the absorbance to a region where you get 0 of the autofluorescence. So then we looked at iron production under antimony as well as growth, and we saw that that Bacillus firmus still grew under antimony stress and produced more IRA. So this gives us a reason for why the plants perform better under antimony stress. And then we did antimony content, and we saw that when you add Bacillus firmus, we decrease the antimony in the roots as well as in the leaves. But we had to answer the question, so does the bacteria take up the antimony, or what happens to the bacteria? And so we showed that Bacillus firmus actually takes up the antimony over time. So when Bacillus firmus formed that association, then when the antimony comes into the plant, Bacillus firmus also take up most of that antimony, and that's why we get the decrease in antimony. So the iron signal that was bugging me, the reason for that was because we saw at 25 degrees, which is our optimal, we saw that Bacillus firmus does not produce siderophore activity. And so we wanted to answer that question. And one of our students that came over to the US came back and she was bored. And so I said, okay, I have something for you to do. This story is bugging me. And I gave her the CB5. And she went and she plated CB5 on siderophore plates, and she incubated it at 37. Right? And there you see siderophore activity. And so that, and then I told her, okay, so this might be a stress response. So let's look at under antimony. And so we looked under antimony at 25, and we could see very nice siderophore activity. And so now we could explain this increase in iron under antimony stress, or we think that is the reason. So where to from here? So we are in the process of sequencing with the iron torrent in South Africa, and then we're going to start this up with David Mendoza over here. And this is not to play the two against each other, but more to come up with good data. And so then we can really target those genes that are important for plant growth responses. And so I already dig into the 5 genomes. And one of the reasons, so why do we need the genomic work, is because these two, the one NDRC, which is closely related to CB5, so the pseudo chitinase, and we wanted to do the dual, where we look at pathogen, how are we going to control pathogens. 2 of them have pseudo chitinases, and this one showed some chitinase activity. So we then plated our bacteria on chitin plates, and we saw no chitinase activity. So, and this is just a positive, how it's supposed to look. So we also had to deal with the fact that Brassica napus, the sequence is not available, the genomic sequence. And I was just also now fed up of working with Brassica napus. So I wanted to work on a model crop, which is also a food crop. So I moved to Phaseolus vulgaris, and we heard over and over and over about vascular diseases. And one of the vascular diseases for common bean is Fusarium wilt. And so the real problem with this is in Africa, in South Africa, is that people harvest this. So they don't look below the soil. So they harvest the green beans, they will eat it as veggies, or they will eat the seeds. And that's a big problem, right? So we really need to control these Fusarium species. And so one of the projects we looked at, we went into the field and we looked for leaves that shows wilt, and we targeted that because our hypothesis was that maybe the plant will form those interactions with bacteria that will have the biocontrol. And so it was a crazy hypothesis, right? And so we found 4 bacteria. One was an Nocardia, Pseudomonas acromobacter, and Stenotrophomonas. And we then had to do the biocontrol assays. So we also did all the other characterization because we wanted to look at plant growth promotion as well as biocontrol. So we saw that all of them produce IA, and this is tryptophan dependent, and none of them had phosphate solubilization. ACE2S, which can also be used to control pathogens, none of them had that activity, and catalase, all of them had catalase activity. So we looked at siderophore because siderophore can also be used to control pathogens because the bacteria will remove the iron before the pathogen can use the iron. And one of our microbes, which the student called Cal for Calvin from the movie Life, right? Showed siderophore activity as well as some of the others. And we think that K2.2 is just sensitive to our siderophore plate. And then we looked at zinc also, and we saw Calvin got slight zinc solubilization, we removed these two because they didn't show any plant growth promoting activity. So we looked at Phaseolus vulgaris series, the cultivar contender, which is being grown in South Africa, throughout South Africa. And we saw that when we add Calvin and all of the others, we see an increase in germination. So that was a good thing. And then we moved on to the biocontrol, where we looked at Fusarium oxysporum, which is one of the severe fungus that causes Fusarium wilt in common bean. And we saw, so we stripped out a block around the Fusarium and we let it grow for 10 to 14 days. And initially, after 10 days, these microbes all blocked in the Fusarium. And my collaborator, as well, who was in the crowd, said, I believe in Fusarium oxysporum. So please give Fusarium oxysporum more time to show you that it can grow outside of that box. And for some, it did. But you can see the control, and there's still some control. So this was one of the, so we grew the common bean in the presence of Fusarium oxysporum, as well as our bacteria. And we saw the student didn't see much responses when she looked at the plants. But I told her, keep on going, and we looked at the pods, and we can see that the pods are much smaller than when we add our bacteria, which was a very good result. So we also looked at all of the other Fusarium to see if we can control those ones. And one of Fusarium calmorum, and we saw that the bacterium can control Fusarium calmorum, as well as proliferatum, and as well as verticilloides, which is a maize pathogen. So the question will be, so what is the reason for these activities? And we thought it would be chitinase. And so we went for the chitinase, and we saw again, we didn't see any chitinase activity. So now we need to look through the other activities to see maybe if it's protease, maybe lipase, and then also couple that to the genes, which will give us more answers. And so with that, I would like to thank the IPG for the invitation, and especially the Center of DST, NRF Center of Excellence in Food Security, for giving us most of the funding, and my collaborators, as well as my MU collaborators, Antia and David, and the students that did the work. Thank you very much.
Thanks, Marshall. So we have time for several questions.
Nice talk. I know in agrobacteria, the genes including auxin biosynthesis localized in the TI plasmid. I wonder where genes including auxin, the bacillus formers in the plasmid or genome. Secondly, if you knock out the genes including auxin biosynthesis or acid degradation genes. So the question is whether the beneficial effect is caused by auxin or acid degradation. If not, maybe other beneficial compounds produced by the bacteria. Thank you.
Thank you. So that's one of the reasons why we are doing the two genomic, the two platforms for sequencing, and that will tell us where the genes are, that it's in the genome, and so from the genome, from the 5 genomes, it's very difficult because you have to look in, like it's the data is huge, right? And because we are moving slow with the genomic sequencing, we are looking at other ways to do the mutations so that we can maybe find a mutant with reduced ACC or reduced IA activity. So thank you. Good.
So for the biocontrol, did you have the bacterial treatment, was that there for the life of the plant, or once it was mature, when would you introduce biocontrol agent?
So the question was the bacterium for the life of the plant. Yes.
So right from germination, you had it in the soil?
I couldn't believe it when I saw it. So yeah. So.
So, actually, a follow-up question on that, does that cause a problem with convincing a consumer to purchase them in the long term? Purchase vegetables that may have beneficial, even though we know it's beneficial bacteria?
So we know that there's many companies that are now moving into making these synthetic. They make bacteria and they put many in a solution and they spray that into plants. So yeah, it will be. I think it will be some difficulty similar to GMO because people will ask what is the negative of those bacteria. For example, Nocardia. Most of the Nocardia species are pathogenic to humans. So I just read a paper last night where they found now a range of Nocardia with plant growth promoting capabilities. So yeah, our finding is not ridiculous. So, but it will be difficult to promote.
If there are no other questions, let's thank Marshall again.